So thank you everyone for this opportunity, and thank you for waiting for me with the technical issues. My name is Jana, and I'm a PhD student of the NEP, and I will talk to you about dust attenuation. So I will mainly talk about how the dust attenuation relates to stellar mass and propose some evolution with redshift. So the short introduction about dust and dust attenuation. Uh, Usually we consider dust to be everything that is not the stars or the gas, so it is the solid matter. And even though it's only 1% of the interstellar medium, it plays a vital role in the cycle of the galaxy. But more importantly, what we're interested in here in this work is how it affects the light, which is why I've shown this beautiful picture of a galaxy where we can see how the light coming out of it has been attenuated, in fact, by the dust. And here, just to tell you a little bit about how we can estimate the dust, I show you a mock ACD of a galaxy with the blue line representing what the light coming out from the stars would look like if there was no dust. However, what we in fact observe is the lower value, so the green line, plus the red. So the light that has been absorbed by the dust is re-emitted in the infrared. And we use this energy balance principle to calculate the infrared excess. And by creating this ratio, we can later convert to dust attenuation. So using this energy balance, we can get some estimate about how much of the light has been, in fact, attenuated. So I want to stress that this is an observational quantity, and it's not, as you can see also on the picture on the left, it's not directly indicative of the amount of dust in the galaxy, but it's a more complicated optical process. What we're interested in more specifically in this work is to find the relation between the dust attenuation or the infrared excess with the stellar mass. So this is something that has been done before, as you can see here on the plot, which is usually what is called the consensus relation. Here you can see that it's been compiled from different literature sources. However, the difference between what is presented here and what I'm about to present to you is that we assume some kind of redshift evolution. Here, all of the data from different redshifts has been compared to each other. So this means that we assume, I mean, they assume that there is no relationship. However, in our work, we do not start from this assumption. And another another goal of our work was to continue this relation for lower stellar masses. So here maybe it goes until 9, but we wanted to go a little bit lower. Here, I would like to take a chance to present the data we were working with. So mainly it was collected from the literature, and as it might be obvious, there are two types of data presented here. So for example, in the top left panel, we can see that there are only a few points. However, in the middle right, there's many points. So the difference is the one on the top left, for example, has been stacked data, and some of the others are data of individual galaxies. So this was our first reason for separating the different data sets in different bins. However, this is not the only separation. We also separated by redshift. So as you can see in some of the panels, there are data from the same papers. However, they are in different redshifts. So in fact, we treated them as a separate bin. And sometimes it is the same redshift, but different paper. So that is also a separate bin. So you can see here that we choose a function that is a line as similar to the consensus. However, with the difference that this line becomes flat at some point. And the explanation for this I will give you a little bit later. And also, I want to point out while I'm still on this plot that even if we use a line, so if we do not decide to make this function flat for lower stellar masses, the fits in most of the cases look more or less the same. So, as I already mentioned, the first thing we did in our work was to separate the data in redshift bins. And the second was to fit with the function that I've shown here. So there are two coefficients in this function. One is where the break happens, so where this function becomes flat, which is the 9.8 value. And another is where this line part that is not flat becomes 0. So this is the 8.7. And in fact, these parameters have been chosen to give overall the lowest chi-square for all of the bins that we used. After we fix these two parameters for all of the bins, we feed again to find this parameter A. And in fact, as you can see the different colors in this plot, this is the different values for the parameter A. The only difference between the functions that I showed in the previous slide are this parameter A. So they all have the same two parameters that I said before, but A is the only one that varies. And in fact, we use this one to model the redshift evolution. We take the value of this parameter and we plot it as a function of the redshift. So we take the redshift of the bin and we take A, and this is exactly what is shown here. Now this is a very nice plot because it looks kind of similar to the cosmic star formation rate. However, we cannot use it because it's just the parameter that I set for this function that I showed you before. In reality, what we would do to represent these results and these functions that we use to model the dust attenuation and stellar mass and this parameter A would be to put the two functions together. So if we take this A and we put it in this function here, we would in fact get a three-dimensional, we would get a surface in a three-dimensional space. So the dust attenuation would be a function of both the stellar mass and the redshift. But neither this plot here of the parameter A, neither this 3D function is something we can compare to the literature. So in fact, what we did was to compute the cosmic dust attenuation. This is just another word for the weighted average of the dust attenuation. So at each redshift, we compute the mass function, and then we compute this function that I told you before. So the dust attenuation as a function of both of these parameters. So at each point, the redshift would be fixed, and we would have the mass function. And if we integrate, as I said, weighted by the mass function to find the average, we get each of these points for different redshifts. And as you can see here, it is very well, and it's in agreement with other work of similar kind. I just want to mention here that the error bars are a little bit misleading because they are, so the gray area is a little bit misleading because in fact this is the errors of the parameters of the fitting. The uncertainties of the mass function is not shown here. So for example, at low redshift around 0, this would have in fact larger uncertainty that is shown here. Now I would like to go back to what I said to explain a little bit this flat part of the function. So let's say I don't use the flat function. So I use adjust the line similar to the consensus one, and I attempt to do this exact same plot. In fact, what I get, well, here it's not so dramatic, but in fact, what I get is 0 everywhere. Even if I only take starting from stellar masses of above 9, so we exclude the low mass objects, for example, where the consensus, there is no relationship or we do not have that much data. Even then, when we compute the average dust attenuation, we cannot get even near to the value that's found in other sources. The explanation for this is the mass function. So I present it here, and you can see that in fact there are a lot of objects with low stellar masses and a lot less with higher masses. So in fact, because this is how we compute the average, so it's weighted by mass, these low mass galaxies dominate the average. So one way is to just take because it is for low mass objects, this also means they are fainter, and we do not have that much data. So we cannot assume any particular shape of this function. So we just assume to be flat. And in fact, this is how we present it. It is a flat function. So it is an average of the dust attenuation of low stellar masses, but we acknowledge that there is a large scatter. However, the average of these galaxies is non-zero. It's a lot more than 0. So this is what this average here shows us, that in fact we do need the low mass galaxies to have some average higher than 0. But it is not just our models that show this. It is in fact supported by some data. So here we can see that around 9 we have in the Whittaker data, we have some objects with higher dust. We can see also in Takeuchi for as low as stellar mass is 7, we have large scatter. So we can see for higher mass objects that there is more constrained relation, and for lower it becomes just scattered and some non-zero value. So we can see that the dust attenuation doesn't really go to 0 for these low mass objects. And what is also interesting is that this kind of results is found by simulations. So again, in both Cousin et al. And Ma et al., they managed to reproduce this relationship between the dust attenuation and stellar mass that has been found in many different work. But we can see for the lower masses that this becomes a lot more scattered. But we can also see that there are objects with even relatively high dust attenuation for these low stellar masses. So in a way, we justify our results to use a flat part of this function, so a kind of average, to explain this part of the dependence between the dust attenuation and stellar mass. So I will just say a few possible explanations, but this is not something that we have studied in very detail. So it's possible that is only the geometry that gives this. So if we can look at this very classical plot from Calzetti, so we have more something like the second case. The stars and the dust are not so very well mixed. And this is possible because of the bursty nature of the star formation. Other explanations are, for example, the different dependence of dust to metal ratio, or the different dust attenuation and metallicity relation. However, it is possible that, in fact, these galaxies have more dust than we would normally expect them to. So there might be a physical explanation, not just an optical one. And this is studied in the recent paper of Burgarella et al. So that it is possible the dust is building very fast in these objects. So just to sum up what I've said so far. First, we cannot, for these low mass objects, we cannot ignore their contribution to the average dust attenuation. So we need to assume some function that is not just simple linear dependence. Another very important conclusion is that we started with the assumption that this A5 star relationship does evolve, and we did get results which are similar to what is found by different authors. So this evolution is necessary to describe the cosmic dust attenuation. And finally, what I've been talking about in the past few slides, the low stellar mass objects do have a non-zero average value for their dust attenuation, but for now we can just say that they have a non-zero average and a large scatter. So thank you again, and thank you for staying for my presentation.
So we have 2 questions on Slack.
Okay.
Matt asks, maybe this dust attenuation going down could be a selection effect because diamond-bearing galaxies are very blue. So samples may be lacking of red galaxies.
Yes, that is true. But in fact, if you look at our data set, we have very few galaxies with low mass here. So yes, it is very likely that it is a selection bias, so that it's, in fact, we do observe only the galaxies who do they have higher dust attenuation. However, to be able to explain this plot, in fact, this is a little bit I don't want to say theoretical, but we do need these low mass objects to have a higher dust attenuation, because on average we observe this cosmic dust attenuation. I don't know if that makes sense. In fact, because we are trying to reconcile these two relationships, so the cosmic dust attenuation with the aeric stellar mass, this is why we have this problem of the low stellar masses. So it's not only coming from the so it's not the only let's say this data is not the only indication, but in fact it is the sources that we have here also that confirm our idea.
All right. So the last question is from Tomo. Is the AB as a function of Z proportional to cosmic star formation rate density expected? Your point of view?
We do expect the dust to follow the star formation rate, because these two processes are very connected. But also, it's not, I think that there is a slight delay. So the peak would not be exactly at the same redshift. But yes, we do expect them to have the same shape.
Okay, he's nodding, so I guess there's no All right, so are there any other questions? If not, then let's thank Jana again.